In this video, we're going to extend our process for evaluating triple integrals and look at what happens if we don't have a nice rectangular box. So basically a non-rectangular solid. Now, let me preface this video by saying in three dimensions, things can get pretty crazy, and we're not about to get pretty crazy. But we have to be able to handle some of the simpler solids that might not be a rectangle, right? So that's what we're going to look at. And first up, before we do an example, I just want to give you some tips as far as like if a triple integral is set up for you. How do we know that this is like a valid triple integral, right? In other words, is it worth even trying to evaluate it? I mean, you could do a process, but is the result going to be meaningful, right? So what does it mean for a triple integral to be valid? Now, in all our work with double, triple integrals, etc., once we evaluate, right, and once we have our limits, our final answer is going to be a number. And that number can represent lots of different things. So let's just look. So we're going to look at some examples, and this is not a list of all of them, right? But I like to just get an idea of what valid triple integrals are. Like, how can we tell just by looking, right? So for instance, if we see a triple integral and all the limits are constant, right, provided we can find our antiderivatives, right, and our goal is not to do crazy integration here, then yeah, we know we can evaluate it. In fact, we have 6 different ways that we can evaluate it, and we'll get our final answer. But what if the limits now start becoming variables themselves, right? So not just numbers, but maybe they'll have our variables in certain expressions. So let's say we're integrating this. So this is our general function. And suppose we are going to choose to use the order dx, dy, dz, right? How bad can this thing be, basically? Right, so this is just our first example of this. Well, if we're going to integrate with respect to x first, worst case scenario is that our first pair of limits could have the other 2 variables in there. So it could be something like, and I'm going to use lots of different letters here, but I'm going to use h, so you could have like h1b, and that could be a function of y and z. And then the limits there could also be a function of y and z, right? Yeah, so if we're going to integrate with respect to x first, for this to be a valid thing, the worst case scenario is the first pair of limits could have the other 2 variables. Because here's what's going to happen. When I integrate with respect to x, and then I plug these 2 functions in and subtract, the expression that I have left would have to be in terms of the other 2 variables, so that when I complete my process, right, eventually I will integrate with respect to y, and the y's will go away. Eventually I will integrate with respect to z's, and then the z's would go away, and then I would be left with a number, right? So if I start with an x, these are what my first pair of limits could look like, right? Then, after I do that integration again, and we would simplify, the second integral would be in terms with respect to y. That means the second pair of limits, right? Because there's only going to be dz left, the second pair of limits could only have the variable z. So you could have something like g1 in terms of z, and then g2 in terms of z, right? Because then after I integrate with respect to y and I plug these in and subtract, all I'm going to have left is z. So then my last integral now, the function that I'll be integrating is going to be dependent only on z, And then the last pair of limits for us is always going to be a pair of constants. So you could do something like e to f or something like that, right? So that's one example of a valid triple integral, right? It looks a lot scarier when you have all these functions in the limits, but you can't just put any function on any limit and have a triple integral. So there are some rules that we have to abide by. Let me give you another example of this. In fact, there are 6 of them because there are 6 ways I could set up my dx, dy, dz. I'm not going to do all 6. I'm just going to do another one, and then you can work on maybe play around with the other 4. Let's say we do the order dz, dx, dy. Why would we do that? I don't know. Maybe because it's Thursday and we do this on Thursdays. Okay, so let's see. If we're going to integrate with respect to z first, then the first pair of limits can only have x's and y's, right? It doesn't have to have both, but we're saying worst case scenario, right? We love it if they were all constants, but that's not always the case. So my lower limit now could be in terms of x and y, and then my upper limit here, again, can be in terms of x and y. And then let me do something that I didn't do on my first example in terms of green. So after you do this process, think about what's going to be left. You're going to do an integral with respect to z, right? So hopefully something that we can do our rules and we integrate. And then we're going to plug in something that has an x and a y and another thing that has an x and a y, and we're going to subtract. So that thing in green is some function of x and y, right? Whatever it is, it's only going to have x's and y's. And then that thing now, we can tell that it's valid because look, we still have to integrate with respect to x, we still have to integrate with respect to y. All right, that's how you can sort of think about it. Like if my limits are of this form, does it make sense to even go on? Am I going to end up with a number at the end? All right. So now let's see what the second pair of limits would have to be, or could be, worst case scenario. So we have now our thing of x and y, and we are going to next integrate with respect to x. That means y is going to be our last variable of integration. So the inner integral here could be in terms of y, because we still have y left to go, right? So then this could be in terms of y, and then that could be in terms of y, and then finally the last pair of limits for us is always going to be a number, and I'm just going to use c and d because I like to use e and f for constants for z, c and d constants for y, and if we were using x as the last variable of integration, I would probably use a and b as my limits. But there you go, right? So I'll just say etc. is even though we're now going to look at things more generally, we can't just put any function anywhere and say, hey, this makes sense. No, there are some rules that we have to abide by. Okay, so we're just going to do one. Again, as I said, we're not going to get super crazy with the non-rectangular solids, but here is a problem that we're going to work through, right? And part of the reason why we're not going to get very crazy is that in order to set these up, we have to be able to visualize these things. And again, it's harder to visualize things in 3D. It's not impossible, but it's harder. So let's say this is what we want to integrate. I'm going to choose a pretty simple function. So it's 2x, really simple, dv. And then here is my thing. And now I'm going to describe what S is. So S is the solid or region, let's see, under the, I'm going to take a very simple kind of surface, under the plane, right? So let me give you the equation of the plane. Let's say it is 2x plus 3y plus z equals 6, and then I would say in the first octant, octant, right? Okay, so this now, so notice we have no limits currently, and we have to make sense of what do we mean by in the first octant, okay? Well, the first octant, just like in two dimensions, how you have quadrants, quadrant one, quadrant two, quadrant three. Quadrant one in two dimensions, both x and y are positive. Um, the first octant in three dimensions, and the reason why it's an oct instead of quad is because there are actually 8 possibilities in terms of whether x and y and z are positive or negative, right? So there are a lot more possibilities. That always happens when you go to 3 dimensions. So the first octant here is where, in fact, let me just do this. So the first octant, this is the part of the XYZ space that we plot where we have those kind of that standard orientation, and that is when x is greater than or equal to 0, and y is greater than or equal to 0, and z is greater than or equal to 0. So when we do something like this, in fact, let me do it over here. When we do something like that, right? And that's our origin, and everything's going in the positive direction. That is the first octant, right? So we've been using it all along. Okay, so let's see if we can sketch this plane, right? Well, one of the nice things about the plane, because it's a flat, it's a linear object. All we need for a plane is really 3 points. If you remember going back when we, you know, applications of the cross product, I believe, and we had to find the equation of a plane, we needed 3 points. Same thing here. If we want to sketch a plane, we just need 3 points. And what we can do is we can use the intercept approach, right? So using intercepts, so let's figure out what are the standard coordinate axes, intercepts for this plane. So like on the x-axis, what do we know? Think about that. What do we know about what happens on the x-axis? Well, y and z are 0. So on the x-axis, y and z are 0. So the equation becomes 2x equals 6. So x equals 3. So this plane intersects the x-axis at the point 3, 0, 0. So I'm just going to plot that point right here. So 1, 2, 3, so right there. All right, and then we do this for each of the other axes. So let's do our y-axis. So what do we know about the y-axis? We know that x and z are 0. So plug those in, and we're left with 3y is equal to 6, so y is equal to 2. So here is the y-intercept of this plane. So 1, 2, so it's right. In fact, let me use a different color here. So there is one, there is another, and then as you can tell, you should be able to tell by this equation that along the z-axis, where x and y are 0, we just get that z is equal to 6. So we don't even have to do a step to solve, right? So the z-intercept of this plane is 0, 0, 6. So 1, 2, 3, 4, 5, 6. So it's right here. So if we connect them, right, it looks like a triangle, but again, it's just a portion of it. So that's the plane right there. And the way the problem is set up, it says that our solid is everything under the plane, right? So think about it. It's under the plane, but it's in the first octant. So we actually have some bounds for z right away. So let's actually start by figuring out the z limits, right? So our z limits, and let me go this way, right? So our z limits. Well, we have one right here. We know that z is always greater than or equal to 0. So that's nice. So, oh, not x, z. So z is greater than or equal to 0. But if I solve my equation for the plane, if we put it in that explicit form, we get that z equals 6 minus 2x plus 3y. And because the question says that this region, this solid, is under the plane, so z can't be any greater than 6 minus 2x. That should be minus 3y, right? So here it is. So in fact, let me put it like this, right? So our z is greater than or equal to 0, but less than or equal to 6 minus 2x minus 3y. So we can put that together, and we have our first pair of limits, right? So we have, yeah, so 6 minus 2x minus 3y, right? Okay, so that basically defines the height of this solid, right? It starts from the xy plane, which is z equals 0, and then it goes up to points on this little rectangular region that you see here, right? Okay, so now we have to figure out the bounds for, or limits for x and y. So now we need to look at this little triangular region in the xy plane. So let me sketch that, and I'm going to go down here. Now I'm just going to sketch, this is kind of, you describe this as the projection of this plane in the xy plane, right? So just like that. But we know the intercepts, right? It's 3 on the x-axis, right there, and then 2 on the y-axis, right there. Yeah, so that portion, in fact, let me use a different color now. So it's here to here. So I'm just gonna sketch that part. So this is the base of our solid, and it will give us the bounds for x and y. And if you notice, if so, it's everything. I'm not shading because I don't want it to get too messy. Just do this. Try not to make it too messy. But this now looks like a non-rectangular region in 2 dimensions. So we can express this as either a type 1 or a type 2. I'm going to choose to have it be a type 1 and have the x limits constant. So x will go from 0 to 3. So put that there, put that there. And then y, I have to figure out the equation of this line, right? So I have to figure out the equation of the line. Well, the nice thing is I know the y-intercept. The y-intercept is 2. I just need to figure out the slope. Well, it's not too hard for you to look for this, because this is saying if you go up, if you go over 3 units in the x, you're going to go down 2 units in the y. So your slope has to be negative 2/3, right? So yeah, we just figured out the equation of that blue line is y equals negative 2/3 x plus 2. So let's now get the limits for y. So here are our y limits. So y goes from the x-axis, which is 0, up to the blue line, which is our negative 2x plus 3 plus 2. So it's 0 less than or equal to y, which is less than or equal to negative 2/3 x plus 2. And then our x limits now are going to be the constants. So our x limits are going to be constants, and x goes from 0 to 3. All right, so let's put this all together now and make sure we set up a valid triple integral, and then see how we can evaluate this, right? So let's write this down here. So three integrals. So the first one, so because I have my, okay, yes, I have my z inequality right here. Since z is in terms of x and y, I am going to put that first. So we're going to integrate with respect to z first. We're going to go from 0 up to 6 minus 2x minus 3y. Remember, the function that I'm integrating is really simple. It's just 2x. And then the first integral is with respect to z. And then the next integral now will be with respect to y. And we're going to put the y limits there. It's going to go from 0 to negative 2/3 x plus 2. And then the last integral will be with respect to x. And we'll go from 0 to 3. All right? And there you go. Right? And this is the type of problem where we could try to set it up differently. For instance, we could have tried to set this up as a type 2 if you wanted. That's valid. It just means that you would have, the order would be dz, dx, dy. But again, you just have to be careful that the right pair of limits correspond with the right variable. Okay, so to evaluate, here's what we're going to do. I'm just going to do them in order, and the first integral that I'm going to do is obviously this one with respect to z. Okay. And then we're going to do y and then x. So first integral, so I'm not going to rewrite it. I'm just going to write down the antiderivative. Now, since we're integrating with respect to z, 2xy is treated as a constant, so that the antiderivative is going to be that constant times z, and then we're going to plug in our limits. So we're going to do this. So 0 to 6 minus 2x minus 3y, and then we'll have 2x, and then times the quantity. When I plug in the upper limit for z, I just replace z with exactly what I have there. And then when I plug 0 in, I'll have 0. So it ends up looking like this. 6 minus 2x minus 3y minus 0. So this simplifies pretty nicely. If we distribute it, we're going to end up getting 12x minus 4x squared minus 6xy. All right? And then we have to integrate this with respect to y. So now we are going to do this integral, and that's going to take a little bit more work. For one, you know, this is a little bit more complicated now, and you know, we have fractional exponents. So let's carefully do that. So I'm just going to look at this and write down the antiderivative with respect to y. And remember, we're going to be treating x as a constant. So we will have 12x as a constant times y. Then we will have minus 4x squared as a constant times y again. And then now this is the only term that has a y. So when we integrate this with respect to y, add 1 to the power, that gives us 2, divide by the new power, so we'll end up getting negative 3x, which is treated as a constant, y squared, and then this goes from 0 to the negative 2/3 x plus 2. All right, so let's see what happens. It's nice when you have a lower limit of 0, because look, every term has a y, so that will cancel out. But now we have to replace all the y's with this expression, so we got to do that carefully. So 12x times the quantity negative 2/3 x plus 2 minus 4x squared times the quantity negative 2/3 x plus 2/3 x plus 2. That's not too bad. And then minus 3x. The issue now is we're going to have to FOIL this out. So negative 2/3 x plus 2 squared. All right. Well, let's do that algebra. So if we distribute the 12x, we will get negative, so what's that? Negative 8x squared. And then plus 24x, like that. And then we'll have positive um, 8x cubed over 3. So 8, or let's just write it 8 thirds x cubed. And then negative 8x squared. And then positive 2x squared. Oh, wait, no. We got to FOIL first. We have to FOIL. So we will have, so let me bring down the negative 3x. And then when we FOIL out the negative 2 thirds x plus 2, we'll have a 4/9 x squared negative 8 thirds x. And then because of that, remember we have to do the 2ab, so multiply these two and multiply by 2, so that will give us negative 8 thirds x, and then square the 2, so we'll have plus 4. All right. All right, so let's see what we have. Negative 8x squared plus 24x plus 8 thirds x cubed minus 8x squared. Now distribute the negative 3x. So that gives us a negative 4 over 3 because the 3 and the 9 get reduced, and then x cubed. And then we have a positive 8x squared, right? Because it got negative times a negative, the 3 cancels out, so a positive 8x squared. And then finally a minus 12x. Wowza. All right, well, let's look at our like terms to see what we have. So for the x cubes, we have 8 thirds minus 4 thirds, so that's 4 thirds x cubed. Let me cross out what we've gotten rid of. So we got that. Then for the x squared, we're just left with the negative 8x squared because we have a negative 8, another negative 8, and then a positive 8x squared. So yeah, we're left with a negative 8x squared. And then for the x, we have 24x minus 12x. So that's a positive 12x. Whew, there we go. So looks good, and hopefully our algebra is good. And then we have one last integral now. Let me go back up to show you, to wrap this monster problem up. We're now going to do the integral with respect to x from 0 to 3, right? And what I would say is the only thing about this that makes it a little bit harder is, the foiling and the algebra. But thankfully, the actual integration isn't super hard, right? So now let's integrate this with respect to x. So this is going to give us, so power rule here, it will give us 1/3 x to the 4th. Power rule here again, minus 8 thirds x cubed. And then power rule again, plus 6x squared. And then that now we evaluate from 0 to 3. So at the upper limit, 3 to the 4th power, what's that, 81 divided by 3, so that's 27, minus, and in 3, so 3 cubed divided by 3, that's 9, and minus 8, so that's minus 72, and then you have 9 times 6, so that's plus 54. And what does that work out to be? I think it just works out to be 9. Is that right? Yeah, that just works out to be 9. At the lower limit, everything is 0, so we are good to go. And that's the value of this triple integral, right? And again, it could, in terms of interpreting this, let me go back all the way up to top now, to the top. So we have our solid, right? Which is it's like a triangular prism, kind of. It's not a regular thing because the sides aren't the same length. But if we assume that the density of this solid is just the function 2x, right? So just double the x coordinate and you'll get the density at every point in this solid. Then its mass is what we just found, of 9 units of mass. All right. So as you can see, even with quote unquote simple non-rectangular solids, it can be a pretty involved process. Not difficult, but just a lot of steps to work through. So hopefully that helped, and we'll see you in the next video.